human factors engineering has been around since prehistoric man first fitted a stick, or a rock, or a bone to his hand, and thereby improved his hunting, his fighting, and even his better living. Our ancestors fashioned more and better weapons and tools, and as they did, the interaction between man and his creations became proportionately more complex. Down through the ages, man has forever been faced with the many problems of containing, controlling, or simply living with his own creations. So far, he had no science or applied engineering for dealing with these problems. In the year 1898, the size and shape of workmen's shovels, through a series of empirical studies, was deemed to be an important factor in determining the optimum weight per shovelful when shoveling a variety of different materials. Thus began the development of a branch of industrial engineering later to be called time and motion studies. The science of human factors engineering was born with our entry into World War II, a war to be fought with technologies never before dreamed possible. Human systems had to interface with weapon systems that demanded more of their operators than a human was able to give. More muscular ability was called for. More sensory and perceptive ability. More judgmental and decision-making ability to be accomplished in shorter and shorter periods of time. Sometimes the demands on human endurance seemed insurmountable. By now, it was acknowledged that an acceptable, if not optimum, integration of the human into the complex machines and technologies brought about by the war was a strategic necessity. Who were best suited for the job? The engineers who built the machines, or the people who flew and operated them? Interestingly, the first experts to tackle the problem were not engineers, but behavioral scientists, physicians, physiologists, anthropometrists, and psychologists. By the end of World War II, human factors engineering had emerged as a specific discipline, and the unique abilities of this new breed of cat, the human factors engineer, were being widely employed throughout the industry and the military. Today, the need for human factors engineers in the Air Force is greater than it's ever been. To help meet this need, the Air Force Academy offers a wide range of courses in the behavioral sciences. Included is a major in behavioral sciences with an emphasis in human factors engineering.
Human factors engineering is also known as engineering psychology, and in Europe it is frequently called ergonomics. Human factors engineering is very much concerned with the incorporation of our knowledge of man's capabilities and limitations in the design of the objects, facilities, and environments in which man lives and works. In this, we wish to optimize the man-machine interface for the enhancement of the functional effectiveness of this man-machine system.
Human factors has been defined as an area of science concerned with the interaction between the human and the technical environment that he or she produces. In this context, think of man, and the term is used in its generic sense, as a sensing, thinking, controlling being. Think of machine as an operational device subject to control and capable of indicating the status and/or results of its performance. Both man and machine operate in an ambient referred to as the working environment. The interaction between man, machine, and the working environment is the subject of all human factors study, research, and development. Because every equipment system, tool, device, or construction involves people and is created for human purposes, It's impossible to imagine any field of human endeavor that would not receive some benefit from human factors engineering. In the Air Force, with human purposes ranging from improved training methods to the conquest of space, the opportunities are without end. Air Force jobs are becoming more and more complex. Along with this is an increasing need to teach more sophisticated skills to more and more people in a shorter time period and at reduced costs. For this reason, it has become a major human factors challenge. At the Air Force Human Resources Laboratory at Lowry Air Force Base, a study aimed at interfacing students more efficiently with advanced teaching technology has been going on for some time. The Advanced Instructional System, AIS, is a computer-managed multimedia system which administers and manages large-scale technical training. The courses represent the full spectrum of Air Force technical training and include inventory management, materiel facilities, precision measuring equipment, and weapons mechanic training. AIS is an individualized, self-paced instructional system. Students progress through a given block of instruction at their own rate, each student taking advantage of his or her own unique learning pattern. In instructional technology, the human factors people have to concern themselves with a wide variety of human factors problems. What is the optimum time period for feedback to the student from the computer? How efficiently does the student interface with the input devices? What is the best mode for the system to present its message to the student? How can information be presented on an interactive terminal display panel so that the student may best respond? Once, maintenance training involved flight line disassembly and reassembly of actual equipment. It was costly, slow, and diverted much valuable hardware from its primary purpose. The evolution from the old to the new in all training methods takes place because human factors people take into consideration the purpose of each training device or method or system, then apply themselves to finding a better design, a better method or system in terms of that purpose. In the Air Force, the whole training effort is based on the systems approach, which makes training an integral part of human factors engineering. A good example of the systems approach can be seen at Williams Air Force Base, Arizona. This is a research device developed for and operated by the Air Force Human Resources Lab. It's the advanced simulator for pilot training. When it first came out in 1975, it was considered to be the Rolls-Royce of simulators, the ultimate in visual and motion systems. From a neutral position, the motion base is capable of providing the all-important initial or onset motion cue. The computer bank creates the visual imagery, flight sounds, and even the voice of the ground control approach controller. The control console monitors the mission. The cockpit is a replica of the T-37 jet trainer cockpit, plus some added features for new experiments in training simulators. In another trainer, the cockpit has been modified to represent an A-10 aircraft and is used to evaluate the transfer of training from the simulator to the cockpit. Pneumatic air cells in the seat and backrest inflate or deflate to help sustain the sensation of G-forces. The thigh panels and even the lap belt tightens or relaxes, contributing further cues to a corresponding flight situation. With the advent of the simulator and the use of computer-generated imagery, a new and challenging field of study has opened up for the human factors engineer, such as how much fidelity or realism in visual flight simulation is required for optimum training. With today's technology, it's quite possible to equip a new generation of flight simulators with visual systems that can create every detail of the outside world with a fidelity comparable to this actual photography. But fidelity is associated with cost. To what extent can we dispense with realism before the training is impaired? In this connection, the human factors engineer must examine the definition of fidelity as it relates to training and cost, as well as the engineer's view of objective reality, with its emphasis on physical events. The human factors engineer must also reassess the subjective reality of the operator, where fidelity is person-centered and concerns only the human perception of events, real or simulated. Bearing in mind that visual simulation offers an opportunity to control up to 90% of the information used to construct the perception of reality. This is an exciting field of research. Studies are continuing to determine to what extent an operator's simulated world can be manipulated before the required information and learned skills are acquired. One of the tasks is to find out what kind of visual perception processing is common to how many people. What are the limitations? Where does the processing break down? Where can the person be fooled? For instance, there's the phi phenomenon. Two lights a certain distance apart. Each blinks alternately. If spacing, intensity, and frequency are just right, the effect is of one light moving back and forth. The viewer has been fooled. Translate the phi phenomenon into a computer-generated image of a moving target, or a simulated situation where you're the target. Here again, the opportunity to manipulate reality in such a way that control is maintained over the subjective mechanisms of the operator is indeed exciting.
See the numbers on the runway? That's where I want your wheels to touch down.
A whole array of opportunities can be imagined, from the simplest undergraduate pilot training task to sophisticated air-to-air training requirements. Data obtained under combat conditions showed that if a fighter pilot survived his first 7 or 8 sorties, his odds for continued survival went up from 10 to 15% to 80%. Today, a student pilot can learn through subjective experience without laying his life on the line. Many studies underway at the various divisions of the Human Resources Lab have a direct bearing on the subjective world of the trainee. For instance, can one learning cue, whether tactile, audio, or visual, substitute for another in simulated training and become associated with a real-world situation? In the real world, the pilot of this aircraft could be experiencing 6, 7, perhaps 8 Gs. At these high G levels, the pilot would have a restricted field of view, or grayout. The pilot would also feel the Gs throughout the entire body. At the Air Force Flight Dynamics Laboratory, studies are constantly being pursued to prepare pilots for the real-world high-G experience and to provide them with a maximum of simulated high-G physical cues, such as vision dimming, weight increase, reduction of movement, controlled respiratory effects, and a host of other factors that tell them when to start muscular straining to help restore blood pressure to the eyes and brain. A part of these studies is designing displays that will go into aircraft of the 1990s. The requirement here is to train air crews on interpreting computer-generated electro-optical displays, which in tomorrow's airplane will be replacing the traditional electromechanical displays of today. From a human factors engineering standpoint, the problem is one of reducing the amount of information processing required of a pilot faced with ever-increasing performance demands. The big question is, how far can the information processing requirements be reduced without sacrificing vital performance standards? Meet the Combi Man. Combi Man is the acronym for Computerized Biomechanical Man Model. This is a three-dimensional computer modeling technique that the human factors engineers at the Aerospace Medical Research Laboratory are developing for the design and evaluation of aircrew stations. Combi Man allows the simulation of variable body sizes of pilots or other crew members within the aircrew station. The computer can also program in or construct around the imaged Combi Man various types of crew stations. How well does the operator fit into the crew station? What can the operator reach within and without the crew station? What can the operator see within the crew station? Adjunct to CombiMan is HECAD, for Human Engineering Computer-Aided Design. HECAD offers a wide range of graphic capabilities to aid the human factors engineer in producing a better designed workstation. Another computer-assisted study at AMRL is directed at providing engineering data to support the design of the real-world Air Force Remotely Piloted Vehicle System, or RPV. This multi-operator RPV simulation is programmed to maintain control of 35 simulated RPVs simultaneously and includes the interaction of our en route and return operators and a terminal operator or pilot. The smooth interfacing of the individual operators with each other and with the remotely piloted vehicle as a team represents a challenging field for human factors research, development, and evaluation. If you have a creative mind and like problem solving in a creative atmosphere, you might enjoy tackling a problem such as this one. The windscreen problem is an interface problem from the standpoint that it's an interface between the pilot and his outside world. The human factors engineer must also take into account the optical variables that can accompany changes in windscreen design.
These curved windshields on the new aircraft have a lot of problems of interest to the human factors engineer. We have reflections, we have double imagery, we have distortions, rainbowing. But one of the more important problems is that caused by the curvature of the windshield. It acts like a lens, and it displaces the target from where it really is. The pilot sees it in one place, but it is really in another place. These errors are large enough to create large gunnery errors with the pilot. In this test, we have aligned the aircraft with a precision grid board. A camera is precisely located in the pilot's eye position. A series of pictures are taken with the canopy in place and out of place, and the intersections of the matrix of the grid is compared in all cases. We have continued this process looking at corrective actions by the contractor to solve this problem. It is this kind of feedback from the test site that provides for fast and effective corrective action.
The new F-16 has been the laboratory for further G studies. With the seat position tilt back increased from a normal 13 degrees to 30 degrees, the brain is placed in lower elevation in respect to the heart. What effect will this have in lowering the loss of blood from the brain associated with blackout? Further, if this should prove to be a partial solution to the problem, will a greater G tolerance be obtained by tilting the pilot back as far as 65 degrees? However, if this should prove to be the ultimate answer, it will create a chain reaction of new problems in cockpit design. A 65-degree tilt-back position will raise the pilot's legs up and into the instrument panel. What does this do to the cockpit? And what happens if the feet are under the panel and the pilot has to eject? Can all the instruments be read with the head in a fixed position, or will it have to be moved? Or can a helmet be designed to give the pilot that information no matter what the position? These problems alone pose tremendous challenges to the human factors engineer. The right solutions can mean future victories in air battles. Something to make us think of Star Wars is a display still in the planning stages called an integrated path controller. The pilot will be shown a computer-generated picture displaying his pre-planned flight path and projected deviations from that flight path. Each pertinent and essential piece of information will be symbolically represented. It's anticipated that all the airspaces and flight paths of our planet will someday be represented as they actually are at the time: night or day, fog, rain or sleet. If an intercept attempt is made by the enemy, the pilot will see that too. Why not? It's all within the grasp of modern technology and the imaginative as well as practical applications of the inspired human factors engineer. Questions for the human factors engineer. How and in what way do protective garments affect performance in extreme situations? How many millions of dollars can plain ordinary stress cost the Air Force each year? At the School of Aerospace Medicine, Brooks Air Force Base, Texas, the total human being is given prime consideration. What makes him tick? How far can he go? How much heat can he stand? Human factors are evaluated in terms of workloads, cycles in stress, and fatigue. Equipment and human capabilities and limitations are evaluated in the terms of the mission to which they apply. Is the interface a mutually supporting one? Protective garments for a chemical defense program. Negative pressure or positive pressure in a breathing mask can be quite stressful. Protective garments for a thermal ground support program. To what degree is performance sacrificed to safety? How much of a workload and how long can it be performed wearing garments of this design? Can they be improved upon? What are the effects on a pilot's performance during low-level desert or tropical flights when excessive heat is generated under a large greenhouse-type canopy? How much does the loss of body weight through dehydration affect the G tolerance? What will his or her survivability be if the crew member is suddenly exposed to a complete vacuum? What will the CO2 tolerance be in a confined spacecraft? What are the key factors in recovering from or reducing the incidence of decompression sickness? Knowing the limitations of the operator, the machine must be designed so as not to exceed those limits. Tool kits in the Air Force of the near future may very well be marked his and hers, or a new generation of tools may be developed to avoid this situation. How does the performance of the female of our species compare with that of the males? In a push-button space age, greater size and weight can become undesirable factors, all other things being equal. New environmental and physiological monitoring techniques are raising the curtain on a startling new world of challenging studies. In any field of work where there is stress, thermal stress or fatigue stress, for whatever reasons, computer-assisted monitoring systems can prove their value in lives and dollars saved. Think of this in terms of accident prevention. Much of the systems analysis work of human factors is done at the Air Force Flight Test Center, Edwards Air Force Base, California. Here, equipment and weapon systems that have already been developed for air and space programs are tested and evaluated. Human factors studies are conducted to determine if a system provides for efficient human performance in its intended operational environment. In other words, the man-machine interaction is evaluated, reported on, and solutions to any existing problems are searched for. Human factors people who may have degrees in aviation engineering, psychology, physics, electronics, or physiology participate in mock-up reviews, preliminary design reviews, and attend conferences with the contract engineers and builders developing the equipment. The earlier that this is done in a project's life cycle, the better, because errors that do not show up until the testing and evaluation phases can cost millions of additional dollars. For that reason, the human factors engineers with the Directorate of Equipment Engineering at Wright-Patterson Air Force Base are integrated into the life cycle of a project from its very beginning. Their job is to write the specifications and requests for the contract proposals, serve on the procurement selection boards, and determine from which contractor the Air Force should buy the required items or systems, and then evaluate the contracts. In addition, these human factors engineers conduct engineering feasibility studies in all areas. They provide the system's project officers with resident human factors expertise and advice, as well as guide the actual development and writing of the OT&E human factors test plans in concert with the Edwards Air Force Base Flight Test Center and the contractor. But the Air Force does not exist by weapons systems alone. Human factors engineering also concerns itself with clothing, face masks, survival gear, tools, special equipment, and so forth. And because of this wide field of human factors challenges existing throughout the Air Force, the need for competent, imaginative, and well-trained human factors engineers is increasing daily. Some of the human factors engineers of the future will be expert pilots or navigators and will hold master's degrees and doctorates to further their skills. Some will have become experts in other chosen fields. Whatever the case, that is why at the United States Air Force Academy, courses that prepare students for this career field are so personally rewarding. Time, technology, and the sciences that will eventually unlock the secrets of the universe are on the march. If mankind is to keep up with these challenging developments, it will be because of the expertise, creative imagination, and devotion of that new breed of cat, the human factors engineer.